In every industrial plant, every cooling loop, every water network, and every gas system, there is one job that must always happen: moving fluids. And for that, we use machines called fluid movers. Fluid movers come in three main categories: pumps, compressors, and fans. They all move fluids, but each one has a different role. Let's break them down. First, pumps move liquids only. Liquids are incompressible, so pumps simply transfer them from one location to another. Compressors move gases only, and unlike pumps, they both transfer and pressurize the gas. Fans also move gases, but they do not pressurize them. A fan only mobilizes or circulates air. It cannot generate significant pressure rise. So far, so good, but pumps and compressors share something important. Both pumps and compressors can be built in two main types. One, dynamic machines. Movement is achieved by throwing the fluid outward. They rely on high-speed rotation to add energy to the fluid. Dynamic machines include axial type. The fluid flows straight along the axis. Centrifugal type. The fluid is flung outward by an impeller. 2. Positive displacement machines. Movement is achieved by trapping pockets of fluid and pushing them forward. Positive displacement machines include rotary, gears, lobes, screws, continuous smooth motion. Reciprocating, pistons pushing back and forth. When we compare these four technologies, there is a clear trend. From highest pressure capability to lowest: 1. Rotary, 2. Reciprocating, 3. Centrifugal, 4. Axial. And for flow rate, the order is exactly reversed. 1. Axial, highest flow, 2. Centrifugal, 3. Reciprocating, 4. Rotary, lowest flow. This is why the most common pumps in the world are centrifugal pumps. The most common gas movers for compressing air or refrigerant are positive displacement compressors. Every fluid mover, pump, compressor, or fan can be described by two main parameters. 1. Flow rate or capacity. 2. Head or differential pressure. Head is simply a way of expressing pressure using height of fluid, P equals ρgh. Now let's go deeper into how pumps actually behave. Someone might think that when you choose a pump, it will simply give you one fixed flow rate and one fixed pressure increase. But that is not true. A pump can operate over a range of pressures and flow rates. This behavior is described by something called the pump performance curve. Let's say our pump has a performance curve that looks like this. Point 1, Q equals 1 teralytics, H equals 10 nim. Point 2, Q equals 2 slek, H equals 9 as point 3, Q equals 3 elvacescent. As the flow rate increases, the head decreases. So which point will the pump actually operate at in your system? To answer this, we need to understand the system curve. The system curve tells us how much head is required for any given flow rate. It depends on pipe length, diameter, valves, fittings, elbows, elevation difference, and especially the square of the flow rate friction losses. The general system curve equation looks like H-text system equals H-text static plus KQ squared, where H-text static equals height difference between suction and discharge, K constant representing friction and losses, Q equals flow rate. Now we have a pump curve telling us what head the pump can supply, a system curve telling us what head the system requires. The pump will operate where these two curves intersect. This point is called the operating point. Change the pump curve changes, the operating point changes. Change the system curve changes, the operating point changes. The operating point is not controlled by the pump alone. It is a balance between what the pump can give and what the system demands. Even though a pump can operate over a wide range, its efficiency changes with flow rate. Typically, the efficiency curve rises, reaches a peak, and then falls again. The peak is called the best efficiency point, or BEP. Working close to the BP is crucial because 1. The pump consumes much less energy. 2. The pump lifetime increases. 3. Vibration, noise, and wear are minimized. If you choose a pump that operates too far from its BP, you waste energy and shorten the pump's life. So choosing the right pump means selecting a performance curve that intersects your system curve near the beep. For positive displacement pumps, life is much simpler. These pumps deliver almost the exact flow rate you select, almost independent of the pressure. But that comes with a responsibility. You must ensure that the pump and the system can withstand the pressure generated. If you choose a pump that can produce extremely high pressure for a low pressure system, you will simply waste money. And you might even damage the system if protections are not installed. And that is how fluid movers work. From pumps to compressors to fans. From dynamic machines that throw fluids to positive displacement machines that trap them. From performance curves to system curves. And from the highest flow to the highest pressure. Fluid movers are everywhere. And now you know exactly how engineers choose and use them.